questions, but if I do get to it. So this is a title of this, and I'm going to go quick through the background stuff, I think. Yes, okay, so what this is all about is about an engineering ontology. What is a world made of? Okay, and one of the ways of getting to this is I started out as a physicist, and once you get into quantum theory, you go like, okay, what is the universe made of then in quantum theory? And it seems to be pretty much unanswerable, or certainly difficult. So the suggestion here is that whatever the idea is that the engineering worldview is actually a bigger tent, and that science will be a special case within that. So we're looking for a post-scientific worldview, and I'm going to argue it's middle ground linked to complementarity. I'm also going to say that thermodynamics is very crucial, and then this unexpected link to quantum theory. So just background again, it's an article on that thing, and it basically saying, and what we're looking for is a post-scientific engineering framework. And the criteria, one of the criteria is that say subsume and supersede. What that means is that everything, all the places where science or scientific areas work, we must be able to explain that, okay, make sense of it. And supersede means essentially that we're going to understand science in a new way. So all the deterministic scientific mechanical theories are going to be special cases within this more general engineering theory. That shouldn't be too surprising from the point of view of quantum theory too, because quantum theory is doing the same thing. Quantum theory says we're post-mechanical. I mean, there is no one mechanics anymore. Okay, this is another thing that's just coming out. So I wrote another one following up on this general idea. What is engineering epistemology? What is engineering knowledge? I very much like Vincenti's stuff, and basically the idea that engineering knowledge comes downstream from science is wrong. And Petrovsky takes it the next step, and he says everything you thought was science is really engineering. I tend to agree with that, but it takes a bit to do it. And also, in doing this, there's a lot of links to American pragmatism and all those guys. People say, what's philosophy of engineering? It's a euphemism for pragmatism. And it sort of is. But pragmatism has so much baggage, I just normally avoid it, because everybody has their opinion on what pragmatism is, and who said this, and who said that. So I just avoid it. But another way to say it is that pragmatism is an early attempt at a philosophy of engineering. Okay, my current project, and I'll get to why this is. This is the genius in Lazare Carnot. If you've never heard of Lazare Carnot, you will hear of Lazare Carnot. He is actually, I'm getting clearer and clearer on why nobody knows about him, because he was the key guy. He was one of the three people running the French Revolution, and it was his decision to take off the head of Louis XVI. And so when the monarchy got back in, they banned all his books and everything. So he was rediscovered by this Princeton historian, Gillespie, and since then more and more stuff. So anyway, I'm currently involved in translating into English, which I've never done. It's three of these major works. Okay, so post-scientific ontology. What is a post-scientific ontology? Well, so they asked Bohr, this question of quantum realism. They asked Bohr, what is reality? What is it made of? And stuff like that. And his statement said, there is no quantum reality. Get over it. And what he's saying there, another way of saying that is that he's saying there's no scientific type of reality there, okay? So now Heisenberg's insight, as I call it, for lack of a better thing, is it's not only the particles and waves that are complementary, but it's the ways of observing them. So if one experimental setup is observing particles and others observing waves, those experimental setups are also complementary. And I can take a step further, the way of setting up that particular experimental setup, the way of setting up another particular seminar, these are ways of acting, they have to be complementary. Okay, but then Broglie comes along and says, well, all phenomena are, if you're looking at particle phenomena, there's a wave aspect. You're looking at wave things, there's a particle aspect, so it's all messed up. So extend that, all experimental designs embody complementary aspects. So if you try and do something one way, it always has a little bit of the other. And so the general push here is that all structures and processes embody complementary aspects. So the just general idea here is going to be that the world is made up of, everything that the world is made up of, and all functions in the world have this complementary dual aspect to them. Bohr didn't miss this. This is his coat of arms. And so it's the things as contraries or complementary. I've been tracing back this, contraries, where does complementary come from? Heisenberg has a great story. He says, the whole uncertainty principle, all this stuff comes from, this is derivable directly from conjugate variables. If you have conjugate variables, you're immediately there. What are conjugates? Conjugates are contraries. And this goes, I'm presenting it to you with the history of science here. This stuff goes back to the Greeks, have all sorts of lists of contraries and stuff like that. It's all complementarity, really. Okay, so my basic thesis in all this is that reality is middle ground. What's it made of? Well, there ain't no stuff there, no eternal stuff. So what is it? Well, and a corollary is that this middle ground reality that we see emerges through a middle way process, middle way design process, if you like. Okay, so I'm going to get into some examples here, and then I'm going to get into deeper stuff. So what does it mean to say middle ground ontology? When I'm attending a soccer match, am I experiencing competition or cooperation? Well, sort of both. Well, these are complementary. So that's the example of a middle ground. The idea that reality is middle ground. Okay. So I take that further, like Michael Oakeshott says, all societies, and you can take human societies, animal societies, bacterial societies, the ecosystem, everything has cooperative and competitive aspects. Try and formulate one that's 100% one, 100% another, complete nonsense. I like a recent book, Neil Ferguson, called The Tower and the Square. It's about hierarchy versus networks, about how systems work, societies, different things like that. And basically, the good he plays them off, and he says, well, this one works, but every network has a hierarchy. Every hierarchy has a network. And he says it's a false dichotomy, which is sort of the same thing I'm saying. Okay, so this is the book a while back. This guy, he was famous. He had his 15 minutes of fame, John Haidt, but he wrote this great book, The Righteous Mind, Why Good People Are Divided by Politics and Religion. And this is one of the implications for systems engineering. So why is it that people are like talking past each other? And how does that happen, and why is that? Well, one of the reasons for that, as I'm suggesting, is the world is in fact made up of complementary aspects. And one of the little images, if you put a bunch of Democrats on an island, they'll soon separate into Republicans and Democrats. Put a bunch of Republicans on an island, they'll certainly separate it. Because both of them have, the way in which the system works is it always has these things going on. So we need to learn, if we become aware of this, which is one of my punchlines down the line. Anyway, so another example of this stuff. The engineering worldview is clearly a systems view. Okay, and hopefully that's not too surprising. But so example of the complementary processes going on. You see, like this, the Earth is non-equilibrium, but it's also enormously stable. It's a homostatic system, as Lovelock and those guys pointed out. So Margulis and Bernadette. So these are complementary processes. So the agenda of the CO2 producers and the agenda of the O2 producers are different. They're not one type. They have opposite types. And there's a great book by Falkowski. A bunch of my friends are working on this origins of life stuff. And he has these bacteria down there at the deep sea vents, and you have like one side of the bacteria are using sulfur at plus 3 valence, and they export it at -5 valence, and the other guys catch it at -5 and use it for some, and their metabolism kick it back at +3. And this is very typical of these little consortia that are all over the place. And this is kind of a mini version of the CO2-O2 thing. He has a great line. He says, the one rule of being part of one of these consortia is you don't outcompete the other side, because you want to have anything to eat. Okay, so these consortia, and it also just chemically, these consortia are also productive. So and same with Earth. Obviously, it's evolving. It's not just a steady state. It's an evolving steady state. Anyway, very, very general ideas like why are things stable? Is because they have these components. Okay, so how does evolution work? Notice it via the middle way. So everything, so all systems evolve through a progressive cumulative balancing optimization. I'm going to try and explain that. That's the pitch. So the biosphere evolves. And evolution is a thermodynamic process. It's not mechanical. Thermodynamics turns out to be crucial to engineering. Engineering worldview is a thermodynamic worldview. Okay, fundamental physics of the thing is thermodynamics, and it's engineering thermodynamics. It's not physics thermodynamics. I'll get to. So evolution as a process is better understood as an engineering enterprise. My friend Bill Martin has this thing going from prokaryotes to eukaryotes. He has this great line. He says, "Well, when the world has eukaryotes," he said Darwin is like tinkering or something, like tinkering sort of thing. He says, the world with eukaryotes is like, the eukaryotes are like a corps of engineers. They're 200,000 times more powerful than any prokaryote. So they have all this capability of doing stuff, and they explore, and they invent things, and they create things, and they do all sorts of stuff. So that's the kind of idea of this, okay? And if you drink the Kool-Aid, then you have to go to the cosmos as engineering price. Obviously, there's a lot of stuff on this. I like John Wheeler's. And part of it is the universe doesn't evolve mechanically, get over it. But the question is if it evolves thermodynamically, what do we mean by that? How does that work? I say it's middle way stuff. Okay. So this is just restating. So in my book, I have this book out if you want a bunch of examples of this, not as advanced as what I'm presenting here in some sense. But the idea to see this in very human terms, I have some buddies that were in grad school or in London, and they were in the war college. I think it's called a peace college in London or something at the time. And they explained to me, very interesting, like, the guy went in and he said, you need to understand that the mindset of the Defense Department and the mindset of the State Department are opposite. The Defense Department is total paranoia. Don't trust anybody under any circumstances at any time. The State Department says, no, make friends with people. Make friends with people. Make friends with people. You take risks when you make friends with people. So the idea is that these are opposite. And my friend, first of all, saying is that they don't work well together. And the ideal thing, the balance, optimization, the way things should operate is that, you don't want to, like, don't worry about people taking over your state or something like that. But you don't want to have no friends. That's not a good place to be. So anyway, so trying to find the balanced judgment in those is basically the lesson of this that would come out of this. Okay, and also the Tao I like the Tao, as you'll see. Bohr likes it too. And I think that part of the Tao is, and this I call it post-rationalist ideologies. One of the problems is if you're like on the Republican or a Democrat thing, you kind of like, well, if I'm on an island and I'm fighting Republicans and Democrats, let's just get rid of the Republicans. We're all Democrats, everything will be cool. Or we're all Republicans, let's get rid of the Democrats. Mistake. Okay, so any ideological, any like iteration of the same thing, that I've got a rational thing, this is how we solve problems. Okay, mistake. So, and that's the way things evolve. So, okay, so this is catching up. Just remind us where we're at. We're going down through this. I wanted to stick that in so we don't get lost. Okay, so what we need now is so I'm going to take this is kind of like a change into some deeper stuff about what is this engineering framework. And in order to get the engineering framework, we need to make a paradigm shift. But the paradigm shift is not just within science, it's a paradigm shift that's going to go to post-science, okay? So we're going like science is going to be like, something that we're going to explain but not embrace. So post-scientific ontology, it must subsume and supersede. And again, it means that I'm going to have to be able to explain everything that science does, but it needs to understand it in a new way. Now, one of the things that comes out, to put this in, is that, so what is reality? One of the things that comes out of the Carnot and stuff is these double negative statements. My friend Raphael Pisano, they're all over the place in engineering. And the same is like, it's not that there are no particles. It's not that there are no waves. And it's not that there isn't any objectivity. Objectivity is an engineering objectivity. There is engineering activity. Reality is there. Particle physics, it's objective, but it's limited. wave mechanics, subjective, but it's limited. So, and there, to say there aren't, I don't know if you're in there, there are no particles. I mean, this is quantum theory. I mean, there are no eternal things there that obey laws by mechanical laws. So, but these statements are really, really interesting, and they're all through Carnot, and Raphael says they're everywhere, and my friend Drago is saying the same thing. So anyway, so now I want to look real quick at the thermodynamics thing. So Atkins, this sort of shocked me when I first got it. Atkins says, well, there are two different approaches to thermodynamics. There was Carnot and all that sort of stuff, and then there was Boltzmann and atoms and stuff like that. And then he shocks me by saying thermodynamics still has both aspects. And I'm like, no, wait a minute. I was told that, that Carnot and the caloric, that was sort of a historical footnote. So it took me 3 years to convince myself that, in fact, there was. There's the Boltzmann camp and there's the engineering camp. My friend Jolanowitz was he said, when I was getting my PhD at Johns Hopkins in chemical engineering, you get the obligatory thermodynamics questions in my PhD orals. He said, if I said anything about particles moving around, he said I would have been looking for a job in real estate. Because the engineering thermodynamics guys, and I went through, it's like, and you look at the textbooks, and they're really different, but they kind of like, they're not sure how to talk about each other. Okay, so, and the big problem is that these are not compatible. Boltzmann and Carnot are not compatible. I'm not going to go into that here, but they aren't. So the suggestion is, Atkins says maybe they're complementary. I don't think so. I think one of them is more general, which I think is engineering thermodynamics, is the more general, and that all the Boltzmann and all that sort of stuff is a huge number of special cases and exceptions and stuff you see in mechanical engineering. I went to a conference with these guys. They're all bringing up the same problems, trying to solve these problems of the mechanical version of engineering. It's like not going to happen. Okay, so here's a big picture thing. Don Cardwell, lots of books in engineering. He's one of the people that understood what really went on in the history of how did we miss all this? And part of it is, like, I was saying, it was like the generals who won the war write the history. You ever heard that one? So here's, we won the war, and this is what history must have been like, right? Okay, well, the generals were basically everybody goes, oh, mechanics is right. Mechanics is the right way of understanding the world. So the history of thermodynamics must be understandable in terms of mechanics, right? And you see this, even Gillespie does it. Goes back and says, well, Carnot's obviously wrong there, and he's obviously wrong there. He's like, wait a minute. So Cardwell says, wait a minute. We need to, now that quantum theory says, wait a minute, mechanics isn't right, isn't the overall framework, we need to rethink this stuff. And this is really a project. So we need to rethink the history of thermodynamics. How did it actually happen? Relationship between Carnot and Clausius. Clausius just screws it up totally. Entropy. I call them part of the entropy cult. Anyway, so and Lazare writes this stuff. He's writing. He starts writing in I think 1783 or something like that. He writes a treatise on the calculus and stuff. And he has this is throwing down the gauntlet, this middle thing, I think. So what I say, throwing the gauntlet, to make it clear that he's not doing mechanics. And so he says, everybody knows there's a trade-off of velocity, time, and power. And this is just like, how do I want to do it? Faster, I want to do it slower? What am I going to maximize? What's going to be my extrema, so to speak, of the how I want to do it? And he's saying, he goes like, like everybody knows this. The engineers know this. The different ways to approach a problem. But he said, I've looked at all the mechanical theories around, and none of them is able to give us an explanation of this. They can't even make sense of the question. So what Carnot is saying is, I need a world. This is all these guys, it's not just Carnot, they're all at the École Polytechnique in the 1750 to 1850 range. And they're all engineers, and not all engineers, they're everybody there. But Legrand, Cauchy, and so forth. And basically what he's saying is, wait a minute, what's the place of the engineer You got the engineers in the world, folks, and that the idea that the physicists are going to say, well, it's all deterministic. Isn't it quaint that the engineers think they can actually change the course of events or restructure reality because no. He said we have to have a worldview. We need a worldview in which I, as an engineer, can operate and yet still be able to make sense of these scientific relations. Okay, so here's the key. Here's one of the guys. So Carnot bases off this guy. And I'm going to stay on Maupertuis comes up with the same principle of least action. There's this controversy at the time, the vis viva controversy, so I'm going to go real quick. So there was this, what's conserved in motion? Is it mv or is it mv squared? So Maupertuis says it's both, okay? And which one's appropriate to a particular setting depends on your choice of frame of reference. It's sort of like saying, is it particles or is it waves? Well, it depends on which one you want. But you have to make a choice, okay? Now, you get a choice. Choice being a crucial thing here. So, and to give you an idea of this, well, it actually works, cool. So what does it say of action? He says all change is an action optimizing two complementary components. So there's the mv and the mv squared. He said it's always a little bit of each in each. Does this sound like quantum theory? Okay. And prior to choice, prior to my choosing, like to look at the particle or to look at the wave, mv or mv squared, it's dualistic, it's indeterminate. And it's more general than any one mechanics. Now, the part of the thing of the least square thing is that you ask yourself a question: what's this? The shortest path between 2 points? Well, it's a straight line, right? No. So you get gravity and stuff. So you calculate. This is a big problem, and everybody talks about it. But you see in this, you've got your horizontal motion, so to speak, and your gravitational motion forces going on at the same time, and it turns out that the shortest time is in fact to the cycloid. And he goes after Fermat, it's initially so. Anyway, this is the thing they're talking about. This leads him to this idea that this is the optimized path, okay? Is the cycloid. The physicists might have a different idea. So Maupertuis, he goes on and he goes like he wants to say all structures and functions of the universe are optimizations of complementary components. And so reality for him is middle ground. I'll go into some more detail. And for him also optimization, so this coming together these things is always an optimization of the two factors. You never get 100% one way, 100% another, so you're always optimizing. And Maupertuis suggests that optimization is some sort of like a solution or something like that. So there's a purpose involved in this. Okay, so a little bit quick history of this. This is really confusing, but what happened was Euler, who's the genius, the mathematician's mathematician, and first of all he says, Maupertuis is right about, look at the orbits of the planets. They're optimized to, keep them to stay in the orbit, and they're for energy and so forth. They're optimized, these two things. That's how orbits work. And he says, Maupertuis is correct, but it's not very useful. Now I've been struggling with this. I understand it now, but I think anyway. So Lagrange develops a useful mechanical version of action and principle of least action. This is confusing. So we have two things going on. We have the mechanical version of action and the principle of least action, and we have the engineering version of these. They're not the same. So the main thing to keep in mind about Lagrange and what they do is it's deterministic and it has conservation and it has symmetry, conservation of energy. Okay, so that they're still operating in a mechanical framework, Lagrange's. Okay, so Maupertuis and Carnot start from this broader picture before I've made a choice. So Lagrange makes a choice of a framework, and then he's mechanical. Great, but okay. So here's my way of trying to get you to understand. So because there are these aspects, in order to investigate, you have to investigate one way or investigate another way. And Pauli has a great quote. It's Pauli to Heisenberg. He says, he's looking at an early version of quantum theory. He goes like, well, here's the deal. You can observe, or I say act or investigate in the P way or in the Q way. But if you try to observe in the Q way, it will make you crazy. Okay, you can't do it at the same time. And that's kind of what Euler was saying about Maupertuis. So Maupertuis, yeah, you're right. The world is P and Q, but if I'm going to investigate and observe, I got to go one or the other. Okay. The implication of this for this approach is that doing science, what we call science, requires a choice of frame of reference, boundary conditions, and so forth. The Genius, I really recommend you read this book. Somebody said the justification of the calculus. I don't know, when I went through it, why do we always assume the functions are continuous? Why do we, So, anyway, he explained, and it's basically the same thing, because my friend Jennifer Cooper-Smith says also, you can't do science without infinitesimal analysis. You can't do it without, you're sort of dampening out one in order to get the other, all right? Long story. So, now what happens is, remember I said there's this, Lagrange has this mechanical version of action, and that dominated Lagrange, Hamilton, all this sort of stuff. A lot of problems with Hamilton and stuff, but nonetheless. So all of a sudden this thing happens, Planck comes up with the quantum of action. And Planck's action is post-mechanical, it's dual, indeterminate, and involves a choice. In order to collapse the wave function, okay? And I got an article, Planck is clearly aware of Maupertuis. He has an article about him, he talks about him, he endorses him, he says Maupertuis is obviously right, da-da-da. One commentator says that Maupertuis was Planck's bedside reading. No. Anyway, Einstein understood action better than Planck did, at least initially, which led to quantum theory and relativity. Let's say this out. These are not two different theories, folks. They're one theory. I'll back up on that later. In a couple minutes. Okay. So I was going to read this real quick. This is Geoffrey West, guru I've been talking about him. And basically he says, optimization principles lie at the very heart of fundamental laws of nature, whether Newton, Maxwell, electromagnetism, the motion formulation, the general mathematical framework, this needs to be minimized because all the laws of physics can be derived from the principle of least action, which, roughly speaking, states that of all the possible configurations of a system can have, that it can follow, it evolves in time, the one that's physically realized is the one that minimizes action, so the one that's optimized, okay? So nature is optimized, and so anyway, it goes through. That's the basic thing. Geoffrey West is no slouch. He's a particle physicist and stuff. So,
Terry, you have 3 minutes left.
I got 3 minutes, so I'm going to go real quick here. So, so Maupertuis just says everything's, and I want to point this out. Optimization is a concept unique to engineering. It doesn't come up in physics. And the reason is, in physics, you have conservation of energy. You only have one thing, okay? But so you don't have to optimize. I mean, maybe, we use those when we're doing engineering, we use physics. But optimization is a concept. Only comes up when you've got two different points of view, or two different frameworks that need to be brought together somehow. Okay. So this is my conclusion, roughly. Middle ground reality is a result of evolution of middle way of optimization. The middle way is simply optimizing. Okay, that's what the middle way is. It's the balance where the Greeks told us everything in its balance, everything in its measure. So basically, all function, all change, and the evolution of all the structure and function of reality is through a purposeful, optimizing, engineering middle way. I could stop there. Well, this is where I was going to start, which is Bucciarelli's deal, where he talks about the problem of the communication of how do the mechanical engineers and electrical engineers, mechanical engineers, particle guys, electrical engineers, wave guys, how do they communicate? There's no analytical solution is one of the conclusions of the thing. So, the solution of solutions for optimization is this guy Galley. Yes, they have a Wikipedia thing on it, but he's kind of crazy. But they've messed it up a little bit. But basically, what Galley says is there's a thing called essentially contested concepts. A whole bunch of what is reality, what is justice, what is and then this guy Connolly comes along and he says, here's the key. Enlightened dialogue begins when the discussants recognize they're dealing with essentially contested complementary design concepts. So if you and I are talking about justice or anything like that, no, you're right, no, I'm going to beat you up. No, the evolution of things and the way the systems evolve, it comes from this enlightened dialogue. When you realize that the person you're talking to and disagrees with you, something like that, has another point of view that has some value that doesn't make sense in terms of your system. So you need to say, my system must be incomplete. They're going to say, oh, my system must be. And then you start the enlightened dialogue. Anyway, I could go more, but I should stop there.
Okay, thanks very much.
Okay. Thank you.
So I propose that we have this dialogue over lunch and coffee
Yes.
break the rest of the day and tomorrow and wait.